till here any doubt?
So far what you have done is you have initialized the modules that we're using, then you have downloaded one file, which is 786 MB.
Yes.
Then you have unzipped it.
Mm-hmm.
And what is ls doing? Listing
ls,
the
yeah,
content.
yep,
Okay.
yep. This is a Linux command.
Yeah. Okay, got it.
Okay. So what I'm doing is after this, uh, I'm checking what are the content I'm having within this pet image directory. Okay. So within this pet image directory, you will have two folders, one for cat, another for dog. Okay. You can manually check also. You'll see that within this pet image directory, you'll have two folders. One folder will have all the images of cat. The other folder will have all the images of dog. Okay. This might take some time to open because the volume of data is huge here. Okay. So this completes your data ingestion part.
Ingestion meaning ingesting the data in our
In your system,
environment.
in
In a
your
system.
environment. Yeah. Yeah.
Okay.
Right. So because typically any data science process will start only if it will have data, right? So getting the data in your system, that part is done.
Okay.
Now coming to the next module, which is data pre-processing. So data pre-processing means pre-processing your data such that when you apply algorithm on top of it, the algorithm will do its job. Okay. So what we are, so when you are dealing with a real life scenario, specifically for images and all, you'll see that some images might be corrupted, or maybe the encoding technique which in images is not uniform, right? So we need to get rid of those images because those images might be a problem when we are training a model, right? So here what we are doing is we are filtering out corrupted images. What I meant by saying corrupted images, so we are filtering all the badly encoded images that do not feature string JFIF. So JFIF is an encoding format. So any image which is not in this particular encoded format, we are not using that image for our um, uh, modeling.
You mean JFIF is like a file extension and we are getting rid of that?
No, I'm saying that GFIF is an encoding technique. So any
Okay.
image which is not encoded by this technique, we are not going to consider that image for our
Consider it.
analysis. Okay.
Okay.
Similarly, you can might set that you're going to only deal with PNG images or JPG images, right?
Yeah.
This is entirely an optional step. It's not really mandatory, but I'm actually giving you feel from uh, real life scenario, because in real life scenario typically this kind of problem does exist. Okay. So this is nothing, this code is doing nothing. It just iterating over all the images. It will checking it is checking the encoding type. If the encoding type is JFIF, then it is keeping it, otherwise it is removing that particular image. Okay, you see that I have used for loop for iterations, and I'm using a remove command for removing that images which is not having this JFIF encoding technique. You see that ultimately I have removed 1590 images from my entire corpus. All right.
But one question, Ashutosh. So above it says filter out corrupted images. So the task that we are doing here
Mm-hmm.
is why we calling it as filtering out corrupted images? I mean, if the encoding technique is a different one,
Yes,
so we are saying that that's corrupted image.
correct, correct.
Okay.
Okay.
Mm.
Now what I'm doing is, now I'm generating my data set here. Okay. So what I'm first of all saying that regardless of my any input size, first of all I have to bring my input in a standard format. So I'm saying that I'll be dealing with it 180 cross 180 image. Okay. Your input can be of different size. One input can be an HD image, another input can be a smaller image, right? So first of all we have to bring down that image in this particular dimensions, 180 cross 180.
So hang on. Now we have some already a data set, right, that we
Yes.
downloaded, right, which has images.
Yes.
Now they might be having some dimensions which we don't know yet,
Yes.
right? They can be, but here when we are saying generate a data set, we are
Mhm.
initializing a variable where we are saying that we will be making those images of this size.
Yes. 180
Okay.
cross 180. And the batch size we will be using is 32. So what I meant by saying batch size, if you'll recall the training process, how it happens is, first of all, you have to do a forward propagation, then you have to do backward propagation, right? And this entire process is called one epoch. One forward pass and one backward pass is called one epoch. Okay. Now batch size 32, that means what? Uh, we
Uh,
Mhm.
you're not audible.
Hello.
Yeah, your voice is breaking. I could not hear anything like last 5-10 seconds what you said.
Okay. Am I audible now? Is it clear now?
Yeah, yeah.
Okay. So this inputs, as you understood, right?
Yes, yes.
Yeah. So this batch size is nothing but it's a size of input which I'll be using for training my model in one epoch. So what I'm saying that I'll be using 32 images, first of all, for doing one forward pass and one backward pass.
32 images.
Yes, 32. Yeah, is a size, is my sample size. So in our theory class, we have always done these iterations by keeping one image at a time, right? First
You
of all,
mean when you were showing the when you were explaining us, you
yes,
always took one image input and explained.
yes, right.
Okay.
But if we'll follow that approach, it will take like a forever time, right?
Yeah.
Because here we are having data in GBs. So what I'm doing is I'll not be doing it for one image at a time. I'll be passing total 32 image at a time for forward pass and backward pass.
Hmm.
You can increase this batch size also. So these are the hyper parameters, I would say. uh, Ideally we keep changing these values and see for which particular value our model is giving the best result. Now what I'm doing is, again, I'm here doing split of my data. One is training data, the other is validation data. So training data, what I'm doing here is I'll assigning some data into my training set, and with the help of training set, I'll train my model, and I'll assigning some data in test validation data set, and I'll check whether the performance of my model is good or bad on test data set. So this test data set and validation data set, they are nothing, they are one and the same thing. Okay.
Can you come again? What is the difference between training? I understand training means you're training the model,
Yeah.
and validation means you're validating how well your model is trained, right?
Correct. So whatever data that will be a part of training data set, that data will be used for training your model. Okay. Now, once we have trained our model, we will be checking the performance of the trained model over validation data set, because validation data set is the one which model has not seen while training itself.
Yeah, validation data is separate, right?
Yeah. So this validation data set will be used for testing the performance of your model.
Okay.
Okay. So what I'm doing is I am keeping 18,728 images on training data set and 4,682 data, I mean images, in validation data set. Always the volume of data that you'll be keeping on training data set will be higher compared to volume of data you'll have in test or validation data set.
So how did this thing got assigned? Like, did you do it somewhere where
Yeah.
you set training to this much and
Yep.
okay,
Here.
split point to yeah, okay.
Right. Okay. Now let us visualize how the data looks like, right? Uh, so what I'm doing is, first of all, I'm checking, I'm displaying the starting 9 images. For that, I'm having just a for loop, which will iterate over the corpus and display the 9 images out of it. So this is how my image looks like, right? So you'll see that this data is not very clean. It's not, I mean, the process data set. This is the real life data set, right? You'll see that the image of person is also there beside this cat, and humans are also there. So it's not really a clean data set. This is how we actually get data when we solve a real life problem.
Yeah.
Okay. Now there's a concept called image augmentation. So what is meant by image augmentation? So if I show you an image of cat, right, you will be easily able to identify that this is a cat. If I invert that image and I'll show you that image, and if I ask you what this image contains, you will be easily able to say that this is an image only, but it's just that this is an inverted image of cat, right? Because we as a human, we have got that sense of intelligence with us, whereas a model do not have that sense of intelligence, right? If you train a model on a cat data set, it will identify cat, but if you'll invert that same image and if you'll ask model now what is that image containing, uh, that model will not be able to identify. Okay, because the pattern has changed, right? So in order to overcome this sort of problem, we do image augmentation. So what we do in image augmentations, we have one image, right? Now we create different version of that image. How we create different version of that image? We will invert that image, we will flip that image, we will rotate that image by 60-degree or 70-degree, right? Or you can say that we are creating a multiple copy of that same image with different orientation. Is this concept clear?
So
Hello?
you're basically changing the orientation of the image in multiple ways
Yes,
and keeping its copies.
yes, yes. Okay, so that
Okay.
model do not get confused even when you'll rotate an image, or you are showing some flipped version of image, it should be able to generate the answer, right? So that is what I'm doing, image augmentations. So here you see, here I have defined two parameter. Here is random flip horizontal, and random rotation is uh, point 0.1. That means it will it will do this random permutation combination. It will flip orientation by any random degree. It will uh, do a vertical flip, it will do a horizontal flip, right? It will just change the orientation and keep multiple copy of same image. Now this is how your image will look when you will do image augmentation, right? So this is, so these all are the same image, it's just that the orientation is different, right? So this is this is a flipped this is a vertical flipped version of this image.
Can you show the code one more once
Yeah,
that you're doing?
yeah. This
So
is the
where
code I am doing augmentation.
where you're flipping it and then so
Yeah.
you're doing two kinds of augmentation here, like you
Ye-
do random dot layers and then
yes, as I
okay.
mentioned, I'm doing flips also, and I'm rotating the image also.
But why did it generate like six, a total of nine, right? That is up to the system to generate how many it
Yeah,
wants.
that is random now. It can,
Uh,
it
Okay.
you can put your own count also, but that will not be any fruitful in any way. So, so this is the augmented image. Okay, these all images I have generated from the same image. It's just that I'm having different versions of the same image with different orientations and different flip.
Okay.
Okay, now what I'm doing is, first of all, I'm standardizing my pixel value. So right now my pixel value is anything between 0 to 255, right? I want to bring this range between 0 to 1. So here I'm doing nothing but just scaling of my images. Okay, that I can easily do, right? We have discussed why it is important. So what I'm doing is um, I'm just simply dividing my in pixels by 255, so that all of my pixel value will be between 0 to 1. Okay, is this part clear? Okay. This part is purely optional. And yeah, this part I'm not talking about because this is really purely optional. Setting a buffer is not really required. Now, next the important thing comes is now we are done with pre-processing module also, right? We have, so what are the two things we did in pre-processing? We have done image augmentations and we have normalized our pixel value between 0 to 1. Okay. Now let us actually come to architecture part. So as I mentioned, there are two ways. One is you can craft your architecture from scratch by yourself. Other is you can use some predefined architecture also, like the one I was talking about, Rested 50 or Inception V3. In this particular article or in this particular lecture, we are going to see how to craft our image architecture from scratch. Okay. So this is a function where we are actually creating our model, right? So so what are the input for this particular part? It takes two input. One is the input size. What will be the size of your image? I mean the dimension of image, which is 180 cross 180. The other thing it takes is the number of classes. So here number of classes is 2, right? Because you want to identify cat and dog, right? Now we have defined our input size here. Okay. Now the important thing comes here is defining the layers. Okay. So how this is happening is, as I mentioned, we will be doing scaling, right? So that scaling part is happening here. The moment I am fetching input in my input layer, first of all, the first operation I'm doing is scaling. I'm making sure all my pixel values between 0 to 1. After that, I'm applying a convolution layer, right? And that convolution layer I'm having with filter dimension 3 cross 3. Total 32 such filter I'm using here. Stride is 2 and padding equal to same means what? I don't want to lose any pixel value. So I'm doing padding such that even after convolution operations, the feature map size will be same.
I'm not able to hear you, Ashutosh.
There is a keyword here.
Hello, am I audible
Hello?
now? Yeah, am I audible?
Yeah, but I think like after rescaling part, can you say
Okay,
that? There I
okay,
was not audible. No, not audible.
okay, okay. Till this part it is clear, right?
Yeah.
Okay. The next part I am doing is I'm creating a convolution layer here. Okay. So what are the specifications I'm having here is I'm having here a kernel of size 3 cross 3 and I'm using 32 such kernel. Okay. Stride is equal to 2 and padding is equal to same. That means what? After doing convolution operation, I want my feature map to have same dimension as input image.
So that means we will apply that padding, right? That you
Yeah.
had shown zeros.
Yep. We are applying padding here.
So same means we are applying.
Yeah. No. Same means what I'm saying is I'm applying padding such that once the feature map will create after convolution operation, the dimension of feature map will be same as my input image. That's why same.
Yeah, but then what will be the padding? Are we not concerned about what is that padding value?
No, that model will figure it itself.
Okay. So
Right?
same means feature map dimensions are going to be same as that of the input image.
Yes.
Okay.
Okay. Right. So after convolution operations, what we are doing is we are doing batch normalization. So batch normalization means what? After convolution operation, again the pixel value will change when we will convolute our input image with kernel.
Hang on. What is batch normalization doing?
Yeah.
The
I'm coming to that part, but
okay.
this part you understood, right?
Yeah. So just one thing I want to understand for all these statements under entry block, in the end, I'm seeing you're putting X in bracket. What
Yeah.
does that mean?
Yep. So this X is nothing but it is uh, your See here, what I'm doing is, here I'm using a data augmentation function, right?
Yeah.
So this thing I'm applying for data augmentation, augmented image also. Getting? This entire thing has to be applied for augmented images also.
Yeah, I got that you are applying it for augmented image, but the way it's written is x equal to this layer dot. I mean, you're calling, in the layer you're calling rescaling, blah blah blah, and then
Mhm.
in the end, everywhere you're putting x, like x is there, right?
Yes.
So it's like your, I mean, there's no dot between that. We are invoking these on x, right?
Mhm.
That's what I'm trying to understand. What does that mean? Between 255 bracket close, and then there is, bracket open, bracket close, x.
Yep. Yep.
So there's nothing in between. So what operation is going on there?
Yep. Yep. Okay. For time being, just ignore this X part. Okay.
Okay.
For time being, just ignore this X part. This will automatically get cleared when we will invoke this function.
Okay.
Okay. All right. So what I said is, after convolution operation, your pixel value is getting changed, right? So that's why we are again doing normalization of my feature map. I want again to keep all the value of my feature map between 0 to 1. That's why I'm applying batch normalization.
Did we do that in the theory part? Like, did you explain that normalization part?
No, because that's not actually required. It is something we are doing just to make sure all the time our scale is uniform. This is not a part of standard architecture. This is what we are doing from our end to speed up the process.
Okay.
Okay.
Like we studied that max min scaling something.
Yes, yes, that part will also come, but this is not pooling, right? This is just something we are normalizing it. We are just keeping our value between 0 to 1.
Okay.
We did for input layer, but once you'll perform the convolution operation, obviously your scale is going to change. So again, in order to keep our scale between 0 to 1, I'm doing here batch normalization.
The scale will change because of the summation, right? Of 3
Yeah.
cross 3 matrix.
Yep.
Yeah. Okay.
Yep. Right. So after batch normalizations, I am applying an activation function here. Activation function is ReLU. Okay. So this is the one convolution operations, right? Now same thing will happen for multiple times. Now once this part is done, again I am performing convolution operation, right? Now I am having same 3 cross 3 kernel, but I am having total 64 such kernels. Again I am doing batch normalizations. Again I'm applying activation function ReLU,
Hmm.
right? Now this process, since I have to do for multiple times, right? That's why I thought of using here for loop instead of I manually writing this multiple times. I'm using a for loop. I've specified size here. Okay, and this size is what? This size will be user defined. Okay, and again I'm doing the same thing for multiple times, right? I'm creating activation function. This separable convolution 2D, I'll talk a bit later. This is not we have something we have seen earlier. Okay. Again, I'm doing batch normalizations. I'm applying activation functions, and then I'm applying a max pooling. So max pooling, we know, right? We are just picking the highest pixel intensity from the neighborhood pixels.
Yeah, but Ashutosh, what does that for size in this list of four numbers? That part is what?
This is the number of kernels, right? So here you'll see that here I'm applying 2D convolution again. So here I'm using a kernel of size 3 cross 3. I'm using total 128 such kernel.
Okay, but initially you did for one, right? Like separately you did.
Yes. Yep.
Or then you are applying for four different values of kernel, right? So
Yes.
this for loop where you're applying, is this happening after this first input layer thing is done and we have some data? right?
Yes.
That is coming after application of all the whatever we did above. On
Yes.
top of that data, we are applying now a kernel of value
Correct.
128, then 456. Okay, right? That's how it
Correct.
is, right?
Correct.
Okay,
Exactly.
okay.
Exactly. If you want to avoid this for loop, you can easily avoid this for loop also, but it's just that here you have to in that case you need to specify the size here explicitly. I do not want to you know, assign this size explicitly. That's why I'm keeping all this size in a for loop.
And also it will be like 4 times you'll be repeating the same thing.
Yes.
Okay.
Right. Okay. All right. So this is how the architecture we create. Uh, Max pooling is applied. See, the sequence is not really important. The sequence you can change also. If you want, you can keep this max pooling layer before also. But this is how these Google people have done. I'm sure there must be some reason of keeping this sequence. They must have done some iterations, and after that, they might have found that this particular sequence is giving the best result. That's why this is the sequence we are seeing here.
When you say sequence, what sequence you're saying? That the sequence of kernel values?
Yeah, value also and sequence also. For example, here you see we are performing a convolution operations, and after doing batch normalization activations, again we are doing convolutions, batch normalizations. They could have placed here max pooling layer after applying activation function.
Yeah. So you're saying whatever based on their experience of
Yes.
the this, they felt that this is how it is doing the better.
Yep. Yes.
Okay.
Exactly. Exactly. Okay. Okay, so see here also we have learned the max pooling, right? They have used here average pooling also. As I mentioned, this thing will come only with some hit and trial, so they might have experienced that doing average pooling is giving better result compared to max pooling, so they used here max pooling here, right? So this is all configurations they have defined for hidden layer, right? Now the coming to the third part, which is the output layer, right? So output layer is what I said, it's mainly a classifier which is classify your representation into one of the several bucket. Now what I'm doing is, if it's a problem binary classifier, what I mean by saying binary classifier, if number of classes is 2, then activation function I'm using is sigmoid. But I'm having a multi-class classification problem, then activation function is softmax. This is what we have discussed, right? uh, when to use softmax functions and when to use sigmoid function.
Yeah, but the question now here comes is when where you're putting this if else condition, right?
Mm-hmm.
Where you're saying that this is the final output.
Mm-hmm.
Now, how doesn't code it tells that this is the final step?
Yeah,
Because I'm no longer applying layers.
because see, this thing I am applying in the last layer, right? This activation function which I'm defining here, I'm applying in the last layer. That is why the model will automatically understand that this last layer is the output layer. Always the last layer will be output layer.
You mean in the sequence of layers, the last layer that we are writing is the output layer,
Yes,
right?
yes.
I mean, is the output.
Yes.
Okay.
Always, not only in this architecture, in any architecture, the first layer will be input layer, the last layer will be output layer. All the game we have to play is in between input layer and output layer.
Hmm.
For
Right?
loop and if statements you have.
Yes. So
Yeah, we came out of else.
yeah.
That's the last one.
Yep. So here, based on this logic, whether it's a problem of multi-class classification or binary classifications, I'll be choosing appropriate activation function. Now, here there's one important thing. There's something called dropout, right? So what is dropout? Dropout is a process where what we do is we randomly switch off some of the neuron. Why we do that? So that our model does not overfit. What will happen, since we are using a very deep neural network, I told that there's a chance of overfitting, right? So in order to avoid overfitting, there's a concept called dropout where we randomly remove neuron from my layer and I'll train, so that the model will not remember the path. It will generalize the data. Okay. If this dropout part is not really clear, I can take a separate module on in theory class also. But for now, you can understand that this dropout is important to prevent overfitting.
To prevent what?
To prevent overfitting.
Overfitting. Okay.
Okay. Overfitting is a scenario where your model, instead of generalizing, it remembers the data, which we don't want. Right.
Okay.
So in order to avoid overfitting, this dropout is used. What we do in dropout is we randomly remove 50% of